Work. In physics, work is said to be done when a force applied on the body displaces the body through a certain distance in the direction of applied force. Here, suppose this is the ground. A body is lying on the ground at position A. If we apply force, say F, and it displaces the body to the another position, say B, the displacement is, say, S, then the work done is force into displacement. Here we see the displacement of the body is in the direction of a force. Now, dimensional formula of work. We know dimensional formula force is mlt minus 2 and displacement L. So we have ml 2t minus 2. This is the dimensional formula of work. In SI unit of work is joule. Now, work is said to be 1 joule if 1 Newton force displaces a body through 1 meter in its own direction. Work done by a constant force. Now let us consider a body lying on the horizontal surface. Let a force F be applied on the body such that the direction of the force makes an angle theta with the horizontal direction. Let the body be displaced through a distance S. Here we see force is acting in this direction. We resolve the force into two components, one along horizontal direction, another along a vertical direction, and its horizontal component is F cos of theta and vertical component is F sin of theta. Now we know that work done is equal to force applied in the horizontal direction into displacement. Now here in this case force in the horizontal direction is F cos of theta and displacement in horizontal direction is S. So we have Fs cos of theta, or we can write like this F dot S. We know that dot product of two vector is A dot B is equal to A B cos of theta. So here we also know that dot product of two quantity is a scalar quantity. It means work is a scalar quantity. Work done in terms of rectangular components of force and displacement. Let us consider a body is placed at origin of a rectangular coordinate system. Let a force F is applied and the body is displaced through a distance S, so that S is x I cap y j cap z k cap, and force f x I cap plus fy j cap plus fz k cap. Fx is the component of force along x-axis, Fy is the component of force along y-axis, and Fz is the component of force along z-axis. Now we know that work done is force into displacement. Here we have Fx I cap plus Fy j cap plus Fz k cap dot x I cap plus y j cap plus z k cap. Now we know that I dot I equal to 1, j dot j 1, and k dot k 1. Work done in terms of rectangular components of force and displacement. Let us consider a object is lying at origin of the rectangular coordinate system. A force F is applied on the object and the object displaces through a distance S, and the coordinate of these points x, y, z, and this is S. Now we know that S equal to x I cap plus y j cap plus z k cap, and force F x I cap plus Fy j cap plus Fz k cap. Fx is the component of force along x-axis, Fy is the component of force along y-axis, and Fz is the component of force along z-axis. Now we know that work done is force into displacement. Here F is Fx I cap plus Fy j cap plus Fz k cap dot x I cap plus y j cap plus z k cap. Now we know that I cap dot I cap is 1, j cap dot j cap is equal to 1, k cap dot k cap equal to 1. As we know that A dot B equal to AB cos of theta. Here I cap dot I cap is equal to magnitude of I cap cos of 0 degree, as angle between I cap and I cap is 0. So we have magnitude of unit vector is 1, magnitude of unit vector is 1, and cos of 0 1, so we get 1. Similarly, I cap dot j cap is equal to magnitude of I cap, magnitude of j cap, cos of 90 degree, as angle between I cap and j cap is 90 degree. Cos 90 is 0, so we get here magnitude is 1, and multiply 0, so we get 0. So we have Fix I cap dot x I cap, we have x Fx plus this term 0 and this 0. So we have next term y Fy plus z Fz. So this is the expression of work done in terms of force and displacement. in its component form. Nature of work done in different situations: positive, negative, zero, work done. Positive work done. We know that work done is equal to Fs cos of theta. If theta is 0 degree, we have work done is equal to Fs cos of 0 degree. We know that cos 0 is 1, so we have Fs. We get the positive work done. It means force and displacement are in a same direction. For example, suppose a body is falling down from B to A. Direction of force is in this direction, and also displacement of the body is in the same direction. So we get the positive work. Another example is here, this is a spring, and if we apply force on this spring and displacement say S, then work done is positive as both force and displacement are in a same direction. Negative work done. Here, if theta is equal to 180 degree, then W is equal to Fs cos of 180 degree. Cos 180 degree is minus 1, so we have minus Fs. It means the angle between force and displacement is 180 degree, and or we can say force and displacement, they are in a opposite direction. For example, here the body is at position say A and it goes from A to B. Here we see displacement of the body is in this direction and force acting is in this direction. So angle between force and displacement is 180 degree. So in this case we say the work done is a negative. And another example is when brakes are applied to stop a moving car, the work done by the braking force is a negative. This is because the direction of the braking force and displacement of the car are opposite. Zero work done. If angle between force and displacement is 90 degree, then work done is 0. Here cos 90 degree is 0, so work done is 0. For example, a person is carrying a suitcase and the force is in this direction and displacement of the suitcase is in this direction. So angle between force and displacement is 90 degree. So work done in this case is 0. Another example is a body is moving in a circular path. The centripetal force is acting along the center and displacement is in this direction. So angle between force and displacement is 90 degree. So work done in this case is also 0. Work done by a variable force. Variable force means a force whose magnitude changes continuously. Let us consider a variable force acting on a body. Let the body be displaced in the direction of the applied force. The graph between force and displacement x is like this. Here we see the force is changing continuously. Now, to calculate the work done by the variable force Fx to displace the body from initial position xi to final position xf, we divide the total displacement of the body into a number of small intervals, each of width delta x. The width delta x is so small that the force Fx is considered constant over the interval. Now the work done is force Fx bar into delta x. Now here we see that Fx represents the height of this portion and delta x is its width. So it means this work done is equal to the area of the strip, of width delta x. To calculate the total work done, we do summation delta w, or we can write like this: summation Fx bar delta x, and this is equal to the area of all the strips between xi and xf. Here we have shown only in one strip, we can show like this, also another strip, and so many strips we can show. If we say delta x approaches to 0, then the number of strips becomes infinitely large, and hence we have w equal to limiting value delta x approaches to 0 summation Fx bar delta x, or we can show like this: w equal to integration xi xf fx dx, or this is equal to the area under the curve between xi and xf. So work done by the force is equal to the area under force and displacement graph.